Lesson 3, Refraction and Lenses. Reading Guide. Key Concepts. Essential Questions. What happens to light as it moves from one transparent substance to another? How do convex lenses and concave lenses affect light? How do eyes detect light and color? Vocabulary. Refraction. Lens. Convex lens. Concave lens. Rod. Cone. Inquiry. Why is its head so big? The cat's head might look gigantic compared to its body, but it is just an illusion. Light can produce interesting effects when it moves from one transparent material, such as glass, to another transparent material, such as water. Why do you think this happens? Refraction of light. Have you ever tried to pick up something from the bottom of a container of water and the object was deeper than you thought it was? This happens because light waves can change direction. Light always travels through empty space at the same speed, 300,000 kilometers per second. Light travels more slowly through a medium, plural, media, such as air, glass, or water. The atoms of the material interact with the light waves and slow them down. Some substances, such as air, only slow light a little. Others, such as glass, slow the light more. As the light moves from one medium into another, its speed changes. If it enters the new medium at an angle, the wave will change direction. The change in direction of a wave as it changes speed while moving from one medium to another is called refraction. Each transparent material has a property called the index of refraction, as shown in Table 1. A medium that has a high index of refraction is sometimes called slow because light moves more slowly through it. A medium that has a relatively low index of refraction, such as air, is called fast. Key concept check. What happens to light as it moves between transparent substances? Moving into a slower medium. Suppose you roll a toy car across a table straight at a piece of fabric. The front tires of the car slow down when they hit the fabric. The car continues to move in a straight line, but more slowly. If you roll the car at an angle, one of the front tires will hit the fabric before the other. That side of the car will slow down, but the rest of the car will continue at the same speed until the other tire hits the fabric. This will cause the car to turn and change direction. As shown in Figure 14, a light wave behaves in a similar way when it moves into a slower medium. Recall that a normal is a line perpendicular to a surface. As light moves into a slower medium at an angle, it changes direction toward the normal. Moving into a faster medium. What happens when light in the figure moves back into the air? Suppose you ride your bike from a sidewalk into a muddy field and then back onto a sidewalk. You use the same energy to pedal the whole time, but you move more slowly in the mud. When you move back onto the sidewalk, you speed up. Similarly, as light moves into a medium with a lower index of refraction, it speeds up. The wave is still at an angle, so the part that leaves the slower medium first speeds up sooner. This causes the wave to turn away from the normal, as shown on the right in Figure 14. You see the boundaries between surfaces such as air, glass, and water because of refraction. If transparent substances have the same index of refraction, you do not see the surfaces. The launch lab at the start of this lesson shows this effect. Lenses. What do binoculars, eyeglasses, your eyes and a camera have in common. Each contains a lens. A lens is a transparent object with at least one curved side that causes light to change direction. Recall that most of the light that strikes a transparent material passes through it. Light refracts as it passes through a lens. The greater the curve of the lens, the more the light refracts. The direction of refraction depends on whether the lens is curved outward or inward. As shown in Figure 15, light passes through two different lenses. A lens that is thicker in the middle than at the edges is a convex lens. Notice that the light rays that move through a convex lens come together or converge. A lens that is thicker at the edges than in the middle is a concave lens. Notice that the light rays spread apart or diverge as they move through a concave lens. Reading check. Describe the shapes of a convex lens and a concave lens. Convex lenses. Have you ever used a magnifying lens to look at a tiny insect? A magnifying lens makes things appear larger. If you look closely, you can see that a magnifying lens is a convex lens because its center is thicker than its edges. The refraction of light by a convex lens is shown in Figure 16. Notice that a normal to the curved surface slants toward the optical axis. Recall that light moving into a slower medium turns toward the normal. As a result, a convex lens refracts light inward and it converges. Focal point and focal length. Similar to a mirror, the point where rays parallel to the optical axis converge after passing through a lens is the focal point. The distance along the optical axis between the lens and the focal point is the focal length of the lens. Because you can look through a lens from either side, a focal point is on both sides of the lens. For a lens with the same curve on both sides, the lens's two focal points are the distance from it. Key concept check. What happens to light as it passes through a convex lens? Types of images. Like a concave mirror, the type of image a convex lens forms depends on the location of the object. A convex lens can form both real and virtual images, as shown in Figure 17. The diagrams show only two rays, but remember that in reality, there are an infinite number of rays. If you look through a magnifying glass at an object more than one focal length from the lens, the image you see is inverted and smaller. If you look at an object less than one focal length from the lens, the image you see is upright and larger. It is virtual because your brain interprets the rays as moving in a straight line, as shown by the dashed lines in Figure 17. Concave lenses. Light rays that pass through a concave lens diverge or spread apart. The drawing on the left in Figure 18 shows why. Notice that a normal to the curved surface slants away from the optical axis. Because light entering a slower medium changes direction toward the normal, the lens refracts light outward. The light diverges. The drawing on the right in Figure 18 shows the type of image a concave lens forms. Suppose you stand to the right of the lens and look at the object. The refracted rays reach your eyes, but your brain assumes the light traveled the straight dashed lines. You see a virtual image smaller than the object. Key concept check. What happens to light as it passes through a concave lens? Refraction and wavelength. You have read that the curved surfaces of lenses affect the refraction of light rays. The wavelength of light also affects the amount of refraction. You might have seen sparkling cut glass ornaments hanging in a window. When sunlight strikes the glass, rainbows appear on the wall. These sun catchers work because different wavelengths of light refract different amounts. You read in Lesson 1 that white light is made up of different colors. A few colors are shown in Figure 19. The speed of a wave in a material is related to its wavelength. Waves with longer wavelengths travel at greater speeds in a material than waves with shorter wavelengths. Therefore, when entering a material, light with longer wavelengths travels faster and refracts less than light with shorter wavelengths. As a result, violet refracts the most because its wavelength is the smallest. Red has the longest wavelength and refracts the least. Prisms. As white light passes through a piece of glass called a prism, each wavelength of light refracts when it enters and again when it leaves. Because each color refracts at a slightly different angle, the colors separate. They spread out into the familiar spectrum, as shown in Figure 20. Rainbows. Why do rainbows appear in the sky only during or after a rain shower? Rainbows form when water droplets in the air refract light like a prism. Each wavelength of light refracts as it enters the droplet, reflects back into the droplet, and refracts again when it leaves the droplet. Notice in Figure 21 that wavelengths of light near the blue end of the spectrum refract more than wavelengths near the red end of the spectrum. This effect produces the separate colors you see in a rainbow. Detecting light. You receive much information about the world around you when objects either emit light or reflect light into your eyes. You have read that the material that makes up an object reacts to various wavelengths of light in different ways. The material absorbs some wavelengths of light. Other wavelengths of light reflect to your eyes, providing information about shapes and colors. Your brain interprets this light energy so that you can recognize the images you see as people, places, and objects. The human eye. Eyes respond quickly to changing conditions. As shown in Figure 22, the iris changes the size of the pupil, which controls the amount of light that enters the eye. The cornea acts as a convex lens and focuses light when it enters the eye. The shape of the cornea cannot change, but the shape of the eye's lens can. Changes to the shape of the lens can alter its focal point. This can enable a person to see objects clearly, either far away or near. Follow the steps in Figure 22 to learn what each part of the eye does that enables a person to see. How the eye works. Number 2. The iris is the colored part of your eye. Number 1. The cornea protects the eye. Light refracts as it enters and as it leaves the cornea. Because air and the cornea have very different indexes of refraction, the greatest change in direction of light rays occurs as light moves into the cornea. Number 2. The iris is the colored part of your eye. The pupil is an opening in the center of the iris that can change size from 2 millimeters to 8 millimeters to let different amounts of light into the eye. Number 3. The lens is convex to help focus incoming light to form an upside-down image on the retina. Number 4. The ciliary muscles change the shape of the lens, making it flatter or rounder, so that you can focus clearly on objects at any distance. Number 5. Cells in the retina absorb light and convert information about the amount of light and color into electric signals. Number 6. Electric signals from the retina travel to the brain through the optic nerve. The brain combines signals from both eyes to produce a three-dimensional, upright image. Seeing color. You might have noticed that it is harder to see colors in dim light. Why does this happen? Different cells on the retina of an eye enable a person to see both colors and shades of gray. A rod is one of many cells in the retina of the eye that responds to low light. There are about 120 million rods in the human retina. Rods enable you to see near the sides of your eyes rather than along the direct line of vision. This type of eyesight is called peripheral vision. A cone is one of many cells in the retina of the eye that respond to colors. The human retina contains 6 million to 7 million cones that require more light to produce signals. These cones respond to red, green, and blue wavelengths of light. Recall that these primary colors of light can combine and form all the other colors. When light strikes a cone, it produces an electric signal that depends on the light's intensity and its wavelength. Your brain combines signals from all rods and cones and forms the colors, the shapes, and the brightness of the objects you see, as shown in Figure 23. Correcting vision. In a person with normal eyesight, the cornea and the lens focus light directly on the retina. This forms a sharp, clear image. Some eyes, however, have an irregular shape. If an eye is too long, light focuses in front of the retina. This person sees near objects clearly, but objects far away are blurred. In other instances, the eye can be too short, and light focuses behind the retina. People with this problem clearly see objects far away, but objects nearby are blurred. Figure 24 shows how manufactured lenses can correct these problems. You have read that refraction and lenses enable you to see. Light can refract as it moves from one medium into another. Different colors refract at different angles. A lens causes light to change direction. An example is the focusing of light onto the retina by the cornea and lens of the eye. Eyeglasses or contact lenses may be needed to help focus this light.